So for starters, we want to refresh our knowledge or introduce you to Torch, which is a machine learning framework from Meta. And you can get it by importing Torch. Maybe you have to install something on your computer, but if you use Colab, it is just there. And in Torch, you do use what is called tensors. And we can create a tensor like this. We grab Torch, and then we say tensor, and we add a number here. So when you do that, you have a number, and I can also put an integer here if I want to. But we are using floating point numbers generally in machine learning. And so I have a number like this. But so why is this called a tensor? And what is a tensor? You might know what a vector is. A vector is a sequence of numbers in some kind of like column or row. And you might know what a matrix is. And a vector is essentially a 1 by n. It is one column and many rows, or one row and many columns. So that is a vertical vector. A matrix has 2 dimensions, but now how you would call something that maybe has 3 dimensions. And so the tensor is just generalizing this idea of having multidimensional data. And so I can also create a vector, if you want, using a tuple notation here. So I put in a tuple, and now when I look at this, I have a vector order. So you can see this when you type shape. So here I get 2 elements. Let's see if this changes anything. If I do that, I should also just get 2 elements. So sometimes you want to actually add this additional dimension, and what you can do is you can use the statement unsqueeze, and you just add it to the tensor that you generate, and now what you get is something that has this additional dimension here. So when you look at the data, it still looks the same, but now you see you have one added bracket here, which tells you that this is just one element in a 2 element or 2 elements in a 1 element vector. So this is very important when you do machine learning, because oftentimes other functions will expect things in a certain format, and you will then need to add dimensions just as you see fit. You can do this again, or I can also add the dimension to the other direction, and so you will get this column vector. All right, so we have a tensor, but now why do we need tensors, or why do we even need to provide numbers in this way instead of just saying x equals like, you know, a tuple or something like this? Well, the reason is because Torch has a function which is called autograd, and right now I just want a very simple tensor which is just 0. And now I can say something called requires grad equals true. And now what this does, this will let Torch compute the gradient of this operation, of any operations you will do with this variable. So, all right, so here it is. You see it is 0, and it will always tell you that this is something where it computes the gradient. All right, so why would you want to do that ever? Okay, so let's consider a function like this, which is a parabola which is shifted by 3. Now let's plot this real quick. Can you please write code to plot y equals x minus 3 squared? And I'm sorry, I'm so lazy, but this is how it's done nowadays. And this will work much better than me making mistakes in front of you. So I just want to visualize this real quick so we can talk about that. And let's keep our fingers crossed. There it is. So you see, this is something that has its minimum shifted to 3. So here is 0, 0, and this whole thing is shifted by 3. All right, so let's think about the problem of finding the minimum of this function. And this is important because this is what machine learning is all about. You have, say, regression or something. You have a prediction over a data set, and you want to minimize the error between what you predict and what the real data says. So these are optimization problems, and we will actually use the exact same tools and methods that we will develop to find the minimum of this. So we can already see the minimum here. But if, let's say, you couldn't see this, maybe this is a neural network which has like 2 billion parameters, and then you don't know the minimum, that's for sure. But let's say you have only the function, and all you can do is play with it to see what happens. So one way of doing this is computing the gradient of the function at some position and moving along the gradient to, or actually against the gradient, in order to arrive at the minimum. So in this case, what we could do is we could say we want to guess the minimum, and we start with x equals 0. So this is what we've done already here. We have been setting x to 0 here. And when we look at the gradient here, we could compute it by taking the derivative, which is 2 times x minus 3. So plug in 0, so it's minus 3, so the gradient is minus 6. And so if I go into the negative direction of the gradient, I would actually go over here. And now I'm as good as before because the gradient here is probably plus 6. And I would then go back and forth. So this is typically an unstable situation. So what you do is you actually move along the gradient, which is called a learning rate. And so, for example, we could say the learning rate should be 0.5. And actually that would be pretty crazy, because then 0.5 times 6 is 3. So we would just jump right from here to there, and we would have our solution. So let's be a little bit less aggressive and set the learning rate to be 0.1. With 0.1, I would get 0.6, so I would move to here, and then I could recompute the gradient. And now I already have to use my calculator here, and I could say what is 0.6 minus 3 times 2, which is the gradient, and it will compute it. It's minus 4.8. Now I multiply this with my learning rate, which was 0.1, and I have minus 0.48. And now, because I'm still lazy, I add my 0.6 to this, and I'm at, actually it was minus 0.6, and I'm at 108 right here. Now I can do this again, and I plug in my 108 here, and I compute the gradient here, and now I also have to subtract, what was it, 0.48, and I would then move to 1.46. So this way I would move toward the gradient. Now let's implement this in Python, and we say the learning rate is 0.1. And let's say I try to do this for 10 steps and just see how, this evolves. So I have y equals x minus 3 times 2. And funny enough, this already just revealed the solution that it thinks I want to choose on using Torch. I can now compute the gradient, and let's call it x grad, and this is 2 times my current x minus 3, and now I can update my x estimate and say x is negative direction of the learning rate times x grad. So it kind of guessed this, and I can print x and x grad. So let's see what happens here. All right, so this is a little error because this is already a torch tensor, and I can actually avoid this by just setting x to be 0. Now it has forgotten about torch, and we will get back to this later. So here you see we are printing x, and it actually converges towards 3. Let's give it a little more, maybe 20 steps. And so you can see here our x is converging toward 3, which is the actual minimum, while this gradient is going down, 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 down. And so, as we know, once the gradient is 0, we actually have reached the optimum. And by the way, of course, you all know I can just set the derivative of this to 0 if I had it. Now, I want to show you how torch can automatically compute the gradient. And it does this when I say that torch is a torch tensor and it's 0 and I require grad. So now we do this again and we get this weird error message. So it says a leaf variable that requires grad is being used in an in-place operation. Where's this? This is here. And so what happens here is I'm actually trying to compute the new value of x as a function of the previous value of x. And then you might say, well, I don't see any x here. Well, of course, x grad is a function of x. So it carries the requires grad thing forward. And we can check this out real quick. We ask x grad, what is this? Is this a number? Just like a typical Python number? No, it's a tensor. And it has a value -6. This is the first gradient that we computed. And it actually even tells us that the last operation that has been done on it was a multiplication, which is this one, which is relevant for the gradient computation. So what you have to do in PyTorch is, if you actually want to update this value, but you don't care about the gradient at this point, you have to put it into some kind of environment where you say with torch no grad. And now I can actually do this and do my computation. Now we are still computing our gradient ourselves, and you see it's the same result. But now I want to show you how Torch can do it for you. So the way this works, it's quite trivial. Instead of computing it myself, I actually say y.backward. And when I do that, it automatically computes something which is called x.grad. And so what happens is x is a tensor that requires grad. Now when I call y backward, it will look at what are all the operations that y has ever been seen. And you can see this here. It actually has this a power function here. That's the last operation that was being done on y. And what this is, it's a computational graph that the Torch implementation will follow and go and see what happened to x from the beginning to the end. And so in this case, you will see that these gradient values here are exactly the same values as we had before. I deleted it now, but you remember the first one was -6. We computed this manually. -6 was the gradient here at this position. And then the gradients become smaller and smaller until they become finally 0. So in this case, we have some overshoot. And so whenever you do this, you will see that things are just raising very quickly. And even if I reduce the learning rate, these numbers will be quite high. And so what actually happens here, the gradient gets accumulated whenever you call y backward. And so what you have to do when you use this approach, you actually have to manually set the gradient to 0. So there's this funny function here, and it has this underscore suggesting you that this is probably not something that you want to use very much. and there are better ways to do it. But this is the way I want you to see that I explicitly have to set this gradient to 0, and then you can see how this again converges to 3, and the gradient becomes very small. So I think I have to print this right here so you actually see the gradient before it gets set to 0. No? All right, so let's do it this way. And so you see here's our gradient goes to 0, and maybe we need 30 steps to really converge to the answer. No? How much do we need? 50? Well, at 50 we have the result that we are looking for, which is 3, but it's still not completely done. Its gradient is still not 0, so it will eventually happen. So quick summary here. The first thing is Torch is able to compute the gradient of a function with respect to its parameters. You don't say y requires grad, but you actually have to tell the dependent variable to be the one that stores the gradient. So in this case, we are interested in dy by dx, and so it's the dx that actually requires grad true. You can have a gradient for y, but that's a different story. So in this case, if you want to have the derivative of a function, the dependent variable is the one that requires the gradient. In order to compute it, you can call backward on any derivative of this. So I could also say, b is 2 times y, and then I can call b dot backward, and it will do the same thing. It will go all the way and compute the gradient with respect to x. Then I have to use this Torch no grad environment so that the gradient is actually not updated when I change the variable itself. So here I want to change the variable. In this case, I haven't changed the variable, I've used the variable. Now I want to change the variable, and that would create a cycle in the computational graph, which is something I don't want to do. So I say, don't compute the gradient for all of the operations in this environment, or in this context. Now, we have the learning rate, we set it to 0.1, and we can see how the gradient eventually goes to 0. It doesn't do this unless we force it to be 0 before we compute it again. And so if we don't do that, you can see here what will happen is the gradient will accumulate. So here the gradient accumulates. Actually, this is very nice. You can see this very nicely here. Remember, this was minus 4.8, this was minus 6. So if I don't reset it, I do get minus 10.8 in the second entry, and then it will keep adding up from here. So now one more thing we could do is we could play with the learning rate. So what do you think happens when I increase the learning rate? Let's say I go up to 0.2. The gradients will be bigger and it will move faster, no? So you see this already here. I'm at a much earlier point in time, and maybe I should just print also the step so you can see where we are at, and you see how things are getting faster and faster. So now we have the result that we're interested in at step 21. Increase the learning rate a little more, and we are now at step 18, and actually at step 19 we are really done because the gradient is 0 and nothing is going to change from here on out. So can we go even further? 0.4, sure, and we are now at step 11 still. Now what happens though if you go higher than this, and this is 0.5, which is kind of the ideal value, it will immediately do it, and everything above that, even this, will create something actually still pretty robust. It caught itself. Let's go 0.8, and you will get something that is unstable, and well, it's still not unstable. Let's go even further. It just takes longer now, and now you have unstable. you get really big numbers. Why? Because it jumps on this curve, it jumps too far out, it jumps even further, and so on. So you will find that in machine learning and all of the problems we have, the learning rate is really critical, because if you set it too slow, it will take much too long for you to train. If you set it too high, it will not converge, and we will learn some powerful tools that Todd provides for adjusting the learning rate normally.